Every star in the universe follows the same fundamental rules: gravity, mass, temperature. These forces define how stars form, how they evolve, and how they die. And in most cases, those rules are consistent. But there are exceptions. Across the universe, astronomers have identified a small number of stars that do not behave as expected. Objects that exceed theoretical limits. Objects that remain stable when they should not. And in some cases, objects that still resist complete explanation. These are not minor anomalies. They are extreme systems that challenge our understanding of stellar physics. And the more closely we study them, the more they reveal gaps in our models. Because if even one of these stars is accurately understood, then something in our current theories is incomplete, or possibly incorrect. In this video, we will examine 7 such stars. Each one represents a different challenge: mass, stability, rotation, and the limits of what a star can become. This is not just a list, it is an investigation into the most extreme stars ever discovered, and what they reveal about the limits of our understanding. There is a question in stellar physics that sounds deceptively simple. How large can a star actually get? It feels like something we should already understand. We have mapped billions of stars across the universe. We have developed detailed models describing how stars form, evolve, and eventually die. At its core, a star is governed by a balance between 2 forces. Gravity pulls inward, trying to compress everything toward the center. Radiation pressure from nuclear fusion pushes outward, resisting that collapse. As long as these forces remain in equilibrium, the star remains stable. And for most stars, that balance holds for millions, sometimes billions of years. But that balance does not last forever. When a massive star begins to exhaust hydrogen in its core, the internal structure changes. The core contracts under its own gravity and heats up. Fusion of heavier elements begins. Helium, then carbon, then oxygen. Each stage burns hotter and faster than the last. As the core becomes more energetic, the outer layers respond by expanding outward. The star grows. Its surface cools. Its color shifts toward red. What was once a compact main-sequence star becomes something far larger, a red supergiant. Stars like Betelgeuse are familiar examples. They are enormous, hundreds of times larger than the Sun, representing a late and unstable phase of stellar evolution. But this expansion has limits. It cannot continue indefinitely. As a star grows larger, gravity at its surface weakens. The outer layers, now thousands of times farther from the core, become loosely bound. Radiation pressure begins to dominate. Stellar winds carry material away into space, and mass loss becomes significant. This process is constrained by a theoretical boundary known as the Hayashi limit, which defines how large and cool a star can become while still maintaining stability. Push beyond this limit, and the star should begin to lose cohesion. Its outer layers should be stripped away. Its radius should decrease. It should not remain in that state. That is the expectation. That is what decades of observation have supported. We see red supergiants. We measure their mass loss. We observe their instability. And in nearly every case, they remain within a range that our physics can explain. Large stars exist, but not beyond the limits of theory. At least, that was the assumption. Roughly 20,000 light-years from Earth, in the direction of the constellation Scutum, lies a region hidden behind dense clouds of interstellar dust. Visible light cannot penetrate it. For most of human history, this region remained invisible. Only with infrared observations were astronomers able to look inside. What they found was a massive stellar cluster filled with extreme objects. Red supergiants, luminous blue variables, stars nearing the end of their lives. But among them, one object stood apart. Not just because of its brightness, although it shines with hundreds of thousands of times the luminosity of the sun. What made it remarkable was something else entirely. Its size. This object has an estimated radius exceeding 2,000 times that of the Sun. To understand that scale, imagine placing it at the center of our solar system. Its outer layers would extend beyond Mercury, beyond Venus, beyond Earth and Mars, past Jupiter, and even beyond Saturn. Every planet from Mercury to Saturn would be inside it, not orbiting it, inside it. At this scale, the concept of a surface begins to lose meaning. The outer layers are diffuse and extended, gradually fading into space. There is no sharp boundary, only a slow transition from star to interstellar medium. Even defining its size requires interpretation. And yet, even with the most conservative estimates, its radius remains far beyond what standard stellar models predict to be stable. And this is where the problem becomes unavoidable. A star this large should not be able to hold itself together. The gravitational binding of its outer layers is too weak. Mass loss at this scale should have stripped those layers away long ago. It should have contracted into a smaller, more stable configuration. It has not. Observations show that it persists in this extreme state, with a surface temperature of roughly 3,200 Kelvin, remarkably cool for a star of this size. This object now has a name, Stephenson 2-18. Even allowing for uncertainty in its measurements, it remains one of the largest stars ever observed. For comparison, Betelgeuse has a radius of roughly 700 to 800 times that of the Sun. Stars like this are not expected to endure. It is likely in the final stage of its life. Over time, it will continue losing mass, its core will exhaust its fuel, and it will eventually collapse, producing a supernova. But its future is not what makes it important. What matters is that it exists now, in a state our models struggle to reproduce. If a star can reach this scale, then the limits we have defined may not be complete. It suggests that our understanding of stellar stability is still evolving, that there are processes, perhaps in energy transport or mass loss, that we have not yet fully captured. This is not a failure of physics. It is a signal, a reminder that even in systems we believe we understand, there are extremes that push beyond expectation. And this is only one example, because elsewhere in the universe, there are stars that challenge not how large a star can become, but something even more fundamental. Not a limit of size, a limit of mass. The first star on this list challenged a physical boundary, a limit of size. An object so vast that its very existence forces us to question how far a star can expand before it loses cohesion entirely. That is a problem of structure, of matter pushed beyond the point where gravity can reasonably contain it. But structure is not the only thing we expect stars to obey. There is another property, more fundamental in some ways, that astronomers depend on perhaps more than any other: brightness. In nearly every branch of stellar astronomy, one of the most reliable characteristics of a star is how much light it produces. A star of a given mass, temperature, and chemical composition will emit a specific, predictable amount of energy. That output may shift over long timescales, thousands, millions of years, as the star evolves. But on shorter timescales, across months or years, a stable main-sequence star should shine with near-perfect consistency. It is one of the most foundational assumptions in observational astrophysics, and for the vast majority of stars ever studied, that assumption holds without exception. This predictability is what makes a technique called photometry so powerful. By carefully measuring how much light a star emits over time, astronomers construct what is known as a light curve, a continuous record of brightness changes across hours, days, or years. Light curves are among the most essential tools in modern astronomy. They detect exoplanets, identify eclipsing binary systems, characterize pulsating variables, and reveal stellar rotation periods. The underlying principle is straightforward. If an object passes between a star and our line of sight, the measured brightness drops. If that object is a planet, the dip is small, clean, and symmetrical. It repeats at regular intervals matching the planet's orbital period. The depth of the dip encodes the size of the transiting body. The spacing between dips reveals its orbital distance. This method has been tested, refined, and applied with extraordinary success across thousands of confirmed planetary systems. It works because stars, as a rule, behave themselves. Between 2009 and 2013, NASA's Kepler Space Telescope stared continuously at a single region of sky in the constellations Cygnus and Lyra, monitoring the brightness of over 150,000 stars simultaneously. Its mission was to find exactly these signals, the subtle, periodic dips caused by planets crossing in front of their host stars. Kepler was extraordinarily effective. It reshaped our understanding of how common planetary systems are throughout the galaxy. But buried within that enormous dataset, among all those well-behaved stars with clean and predictable light curves, one star was producing something that did not look like anything astronomers had seen before. The fluctuations were not subtle. They were not marginal. Something was blocking a significant portion of this star's light, and whatever was responsible did not match the signature of any known astronomical phenomenon. The dips were irregular. They followed no repeating schedule. Some were minor, a brightness drop of less than 1%, barely distinguishable from noise. Others were severe, with the star's observed output falling by as much as 22% over just a few days. To appreciate that number, consider this. A Jupiter-sized planet transiting a Sun-like star blocks roughly 1% of its light. 1%. Whatever was causing these events was obscuring light on a scale that no planet could account for. And the absence of any pattern made the problem significantly harder to resolve. The dips appeared at uneven intervals. Some lasted days, others stretched across weeks. No periodicity, no repeating structure, no symmetry in the light curve, nothing that corresponded to any known category of stellar variability. Not a transiting planet, not a binary companion, not any recognized class of variable star. The data was reprocessed, instruments were verified, independent research teams analyzed the same observations and reached the same conclusion. The signal was real, and it had no conventional explanation. The star sits approximately 1,400 light-years from Earth in the constellation Cygnus. In the Kepler Input Catalog, it carries the designation KIC 8462852. Spectrally, it is an F-type main-sequence star, slightly larger, hotter, and more luminous than our Sun, but in every other measurable respect, completely ordinary. Its chemical composition is unremarkable. Its spectrum shows no obvious abnormality. By every standard diagnostic, this should be a quiet, stable, predictable star. It became widely known by a different name, Tabby's star, after astronomer Tabitha Boyajian, who led the team that first brought its anomalous behavior to the broader scientific community. What her team published in 2016 was not an answer. It was a carefully documented description of a problem no one could solve. Something was happening to this star, and no existing model could explain what. The reason Tabby's star remains such a persistent challenge is not simply that it dims. Brightness variations are well documented across many stellar classes. Eclipsing binaries dim when one star moves in front of another. Cepheid variables pulsate with clockwork regularity. Transiting exoplanets produce small, periodic drops that repeat with each orbit. Tabby's star follows none of these rules. The dimming events are aperiodic. They do not repeat. The depth of each event varies dramatically from one occurrence to the next. And perhaps most troublingly, analysis of archival photographic data stretching back more than a century suggests that the star's overall baseline brightness has been slowly and steadily declining across decades. No single known mechanism accounts for all of these features simultaneously. A transiting planet cannot block 22% of a star's light, regardless of its size. A circumstellar debris disk would produce a measurable infrared excess, which has not been conclusively detected. A stellar companion would leave unmistakable spectral signatures. None of these explanations survive contact with the full body of evidence. In the years since the anomaly was first reported, dozens of hypotheses have been proposed and tested. One of the more widely considered involves a swarm of comets or comet fragments in highly eccentric orbits. As these bodies approach and begin to disintegrate, they could generate irregular clouds of dust and debris, each one different in size and density, producing the kind of uneven, non-periodic dimming seen in the Kepler data. Another proposal suggests that a large, diffuse cloud of interstellar material, entirely unrelated to the star, may be slowly crossing our line of sight, partially obscuring its light over months and years. Others point to the expanding remnants of a recent collision between planetary bodies, a debris field still spreading and thinning. Each of these scenarios accounts for some portion of the observations. None accounts for all of it. And then there is the hypothesis that drew the most public attention. The possibility that the dimming is caused by large artificial structures in orbit around the star. Megascale engineering, the work of a technologically advanced civilization. This idea has been treated as a formally testable scientific hypothesis, and it has produced no supporting evidence. No artificial signals have been detected. No structural periodicity consistent with constructed objects has appeared in the data. It remains open in the technical sense, unsupported in every practical one. What we are left with is a star studied in extraordinary detail, from multiple instruments across multiple decades of data, and we still cannot fully explain it. That unresolved status is itself significant. Tabby's star does not just present an unsolved puzzle, it exposes a gap in the observational framework we rely on. Every star in the universe rotates. This is not a peculiarity. It is a consequence of how stars form. When a cloud of gas and dust collapses under its own gravity, it does not fall inward perfectly symmetrically. There is always some residual angular momentum, a slight inherited spin from the original motion of that collapsing material. As the cloud contracts, that spin accelerates. The same principle that causes a figure skater to spin faster when pulling their arms inward operates at the scale of stellar formation. The result is that every star, from the smallest red dwarf to the most massive blue supergiant, rotates. Some slowly, some quickly, but all of them rotate within limits that physics defines with reasonable precision. And those limits exist for a very specific reason. Rotation and gravity are in constant competition inside a star. Gravity pulls material inward toward the center. Rotation, through centrifugal effect, pushes material outward at the equator. In a stable star, gravity wins. The inward pull is strong enough to keep the star's structure intact, regardless of how fast its surface is moving. But that relationship has a breaking point. As rotational velocity increases, the outward force at the equator grows. At some critical threshold, that outward force begins to approach the strength of gravity at the stellar surface. Push past that point, and the star can no longer hold its own equatorial material in place. Gas begins to escape from the surface. The star starts shedding mass from its midsection. If the rotation continues to accelerate beyond that threshold, the star does not simply lose a little material. It begins to structurally fail. The equator expands. The star distorts into an increasingly flattened shape. And in the most extreme theoretical cases, it tears apart entirely. This threshold is known as the breakup velocity, and it represents one of the hardest physical limits in stellar physics. For most stars, reaching the breakup velocity is essentially impossible under normal conditions. Stellar winds, magnetic braking, and the sheer mass of the outer layers all act as natural governors on rotation rate. Even the fastest known main-sequence stars rotate at speeds well below the point of structural failure. Our own Sun completes one full rotation in approximately 25 days at its equator. The fastest rotating main-sequence stars complete a rotation in under a day, which sounds rapid by human standards, but still places them comfortably within stable limits. The breakup problem, then, is largely theoretical for ordinary stars. A hard boundary that models define, but nature, in most cases, respects. Most cases. To find stars where rotation becomes genuinely extreme, you have to look beyond ordinary stellar physics entirely. You have to look at what remains after a massive star dies. When a star significantly more massive than our Sun exhausts its nuclear fuel, the core collapses. In a matter of seconds, a volume of material comparable to the mass of our Sun is compressed into a sphere roughly 20 to 25 kilometers across. That is smaller than many cities on Earth. The density at this point is almost incomprehensible. A single teaspoon of this material would weigh hundreds of millions of metric tons. Electrons and protons are crushed together into neutrons, producing an object held up not by gas pressure or radiation, but by quantum mechanical resistance, a property of neutron matter known as degeneracy pressure. The result is a neutron star. And a neutron star does not simply inherit the rotation of its parent star. It amplifies it. The same conservation of angular momentum that spins up a collapsing gas cloud operates here, but at an incomparably more extreme scale. A stellar core that was rotating relatively slowly before collapse becomes, after compression into a neutron star, an object that can spin hundreds of times per second. Hundreds of full rotations every single second. And some neutron stars, under the right conditions, can be pushed even further than that. Neutron stars that rotate with extreme regularity emit beams of electromagnetic radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse. If Earth happens to lie in the path of those beams, we detect a pulse of radiation arriving with extraordinary precision at each rotation. These objects are called pulsars, and it is through pulsar timing, measuring the arrival of those pulses with atomic clock precision, that astronomers can determine exactly how fast a neutron star is spinning. Most pulsars rotate between a few times per second and a few hundred times per second, but a subclass known as millisecond pulsars rotates far faster, completing hundreds of rotations every second. They represent the upper range of what we believe neutron star physics can sustain. Or rather, what we believed. In 2006, astronomers analyzing pulsar data from the globular cluster Terzan 5, located roughly 18,000 light-years from Earth in the constellation Sagittarius, identified a signal unlike anything previously recorded. The pulsar, designated PSRJ1748-2446 AD, was rotating at 716 times per second. Not 716 rotations per minute, per second. In the time it takes a human heart to beat once, this object completes more than 700 full rotations. Its equatorial surface, given its estimated radius, is moving at approximately 24% of the speed of light. This is the fastest rotating neutron star ever confirmed, and it sits uncomfortably close to the theoretical limit beyond which even neutron star matter cannot remain intact. To understand why this presents a genuine physical problem, you need to consider what a neutron star actually is. These are not ordinary stellar remnants. They are among the densest objects in the known universe, held together by the strongest force available to normal matter, neutron degeneracy pressure, supplemented in some models by additional quantum effects at extreme densities. Even so, there is a rotation rate beyond which even this extraordinarily strong internal pressure cannot counteract the centrifugal forces tearing at the equator. Theoretical models place this breakup limit for a typical neutron star somewhere between 1,000 and 1,500 rotations per second, depending on the equation of state used to describe neutron star matter. It, at 716 rotations per second, sits at roughly half that upper estimate. That might sound like a comfortable margin. It is not. Because the equation of state of neutron star matter, the precise relationship between density, pressure, and composition deep inside these objects, is one of the most poorly constrained problems in modern physics. We do not know with certainty what neutron stars are made of at their innermost cores. Some models suggest exotic forms of matter may exist there, quark matter, strange matter, or other states that have never been directly observed. Depending on which model is correct, the actual breakup limit for a neutron star like this one could be significantly lower than the theoretical upper bound. It is entirely possible that this object is spinning far closer to its own personal destruction threshold than the average estimate suggests. The question of how it reached this rotation rate is itself a significant area of investigation. Neutron stars are not born spinning this fast. The compression of a collapsing stellar core can produce rotation rates of hundreds of times per second, but not 700. To reach that speed, something external must have intervened. The leading explanation involves a process called accretion spin-up. If a neutron star exists in a binary system with a companion star, it can gravitationally draw material from that companion over millions of years. As that material spirals inward toward the neutron star's surface, it carries angular momentum with it. Each increment of accreted material adds a small rotational push. Over sufficient time, millions, sometimes hundreds of millions of years, this process can accelerate a neutron star's rotation from manageable speeds to the extreme values we observe in millisecond pulsars. This mechanism is well established in principle and is the accepted explanation for the millisecond pulsar population as a whole. But at 716 rotations per second, this object pushes this process to its observable extreme. The accretion would need to have been sustained over an enormous duration, with conditions favorable enough to continuously add angular momentum without triggering instabilities that might slow the rotation or destroy the system. The fact that it exists at this speed is in itself a statement about how precisely certain conditions must align for such an object to form and survive. What this object ultimately demonstrates is that our understanding of matter under extreme conditions is still incomplete. Neutron stars are laboratories for physics that cannot be reproduced on Earth. The pressures, densities, and rotation rates involved exceed anything accessible in any experiment we can currently design. Every millisecond pulsar we study, and this one in particular, provides a data point that constrains or challenges theoretical models of dense matter behavior. The fact that it exists near what some models predict as a structural limit means that the models themselves are being tested every time we observe it. And so far, those models have not produced a complete explanation. We can describe the spin-up mechanism in broad terms. We can calculate what the breakup threshold should be within a range. But the exact internal structure of this object, the precise composition of its core, and exactly how close it sits to its own rotational limit, these remain open questions. Not because the data is insufficient, but because the physics at this scale is genuinely not yet fully understood. But rotation, as extreme as it is in this case, still operates within the framework of mechanics. It is governed by forces we recognize, even if the conditions exceed what we can easily model. The next object on this list operates in a regime that goes beyond that, beyond extreme rotation, beyond structural limits, into a domain of physics where the very forces that govern matter at the atomic level are being distorted by something almost unimaginable in scale. A magnetic field so powerful it can alter the structure of individual atoms from thousands of kilometers away. An object whose existence represents not just an extreme, but an entirely separate category of stellar physics, and one of the most violent environments in the known universe. Rotation, as extreme as it becomes in the case of a neutron star spinning 700 times per second, is still a mechanical phenomenon. It is governed by forces we understand: angular momentum, centrifugal acceleration, the tensile limits of dense matter. The physics are difficult to model at that scale, but the framework is familiar. What comes next operates in a different domain entirely, because beyond the limits of size, beyond the limits of mass, beyond the threshold of rotation, there is another fundamental property of stars that carries its own set of hard boundaries: magnetic fields. Every star generates one. Every star is constrained by the same basic physical principles that determine how strong that field can become and what it can do to the surrounding environment. And for most of the history of astrophysics, those constraints seemed entirely sufficient to describe what we observed. They are not. Magnetic fields are a universal feature of stars. They arise from the motion of electrically charged plasma inside the stellar interior, a process called the dynamo effect. As conducting material moves and rotates within the star, it generates and sustains a magnetic field that extends from the interior out into the space surrounding it. Our own sun has a magnetic field that drives sunspots, solar flares, and the vast arching structures of plasma known as coronal loops. During periods of peak activity, the sun can produce flares energetic enough to disrupt satellite communications and power grids on Earth. By any ordinary standard, these are powerful events. But the sun's magnetic field, measured at its surface, sits at around 1 to 3 millitesla during active periods, a value that, in the context of what exists elsewhere in the universe, is almost negligibly small. For a magnetic field to affect matter directly, it needs to reach a very specific threshold. Below that threshold, a field can influence plasma, ionized gas, by guiding the motion of charged particles along magnetic field lines. This is the regime that stellar magnetic fields normally occupy. They shape the behavior of charged material, channel energy, and drive surface activity. But they do not reach into the fundamental structure of matter itself. Atoms, at the scales of magnetic fields produced by normal stars, are essentially unaffected internally. The electrons in their orbitals are not meaningfully disturbed. The atomic geometry remains intact. There is an implicit assumption embedded in our models of stellar physics that magnetic fields, no matter how strong, remain tools for organizing plasma rather than instruments capable of restructuring matter at the quantum level. That assumption holds for every class of star we commonly study. And then there are neutron stars. Neutron stars, as discussed, are objects of extraordinary density and compactness. When the core of a massive star collapses, the resulting neutron star inherits and amplifies not only the rotation of its progenitor, but also its magnetic field. The compression of the collapsing core concentrates whatever magnetic flux was present in the original stellar material into a region billions of times smaller in volume. The result is a magnetic field strength that can exceed anything found in ordinary stellar environments by many orders of magnitude. Most neutron stars have surface magnetic fields measuring around 100 million Tesla, already a value so far beyond anything produced in a laboratory that direct comparison becomes almost meaningless. For context, the strongest sustained magnetic fields ever produced in controlled laboratory settings on Earth measure around 45 Tesla. A typical neutron star's field exceeds that by a factor of roughly 2 million. But even among neutron stars, there is a subclass that operates at an entirely different level. A rare category of objects where the magnetic field is not merely extreme by neutron star standards, but extreme by any standard that currently exists in physics. These objects are called magnetars, and one of them, in particular, has produced observations that remain among the most extreme ever recorded in the history of astronomy. Located approximately 50,000 light-years from Earth, near the boundary of our galaxy in the direction of the constellation Sagittarius, sits an object designated SGR 1806-20. The letters SGR stand for Soft Gamma Repeater, a class of objects identified by their tendency to emit repeated bursts of gamma radiation. It is a neutron star, but its magnetic field places it in a category that requires its own framework to describe. Measurements indicate that its surface magnetic field strength reaches approximately 100 trillion Gauss, or, equivalently, around 10 billion Tesla. That is roughly 1 quadrillion times stronger than Earth's magnetic field. It is the strongest magnetic field ever measured around any object in the known universe. And at that strength, the field does not merely influence plasma or guide the motion of charged particles. It begins to do something that should, by ordinary physics, be impossible. At field strengths above approximately 440 million Tesla, a threshold known as the quantum critical field, something fundamental changes in how matter behaves. At this level, the magnetic field becomes strong enough to directly distort the electron orbitals within individual atoms. The geometry of atomic structure, the spatial arrangement of electrons around a nucleus, is no longer determined solely by electromagnetic interactions between the electron and the proton. The external magnetic field contributes a force comparable in magnitude to the internal atomic forces. Atoms near the surface of this object are not spherical, as they would be in the absence of the field. They are elongated, stretched into narrow cylinders aligned along the magnetic field lines. The chemical behavior of these distorted atoms is fundamentally different from anything we can study in a laboratory. The material on and near the surface of this object does not behave according to the atomic physics we use to describe every other environment in the known universe. It obeys a modified set of rules that quantum electrodynamics predicts, but that we have never been able to directly test or verify under controlled conditions. This is not just an extreme object. It is a natural experiment in physics that lies beyond the reach of any instrument we can build on Earth. On December 27, 2004, it produced an event that, even by Magnetar standards, was extraordinary. In approximately 0.2 of a second, it released more energy than our Sun emits across an entire 250,000 years of continuous output. The burst consisted primarily of gamma rays and X-rays, radiating outward from the magnetar's surface in a catastrophic discharge of magnetic energy. When this pulse of radiation reached Earth, having traveled 50,000 light-years to get here, it was still energetic enough to measurably ionize the upper atmosphere. Instruments on multiple satellites were saturated simultaneously. radio astronomers detected secondary effects in the ionosphere. The event lasted less than a second at peak intensity. The energy released in that fraction of a second exceeded the combined output of every star in our galaxy during that same interval. Not the Sun, every star in the Milky Way combined. In less than a second. This was not a gradual process. It was an instantaneous reconfiguration of magnetic energy on a scale that currently sits at the upper boundary of what we have ever directly observed in the universe. The mechanism behind this event is understood in broad outline. Magnetars are not static objects. Their extreme magnetic fields generate enormous stresses within the solid crust of the neutron star. Over time, as the field evolves and shifts, those stresses build to a breaking point. The crust fractures, a starquake. The sudden reconfiguration of the magnetic field releases the accumulated energy in a gamma-ray flare. In 2004, that release was not a minor adjustment. It was a catastrophic restructuring of the magnetic field across a significant fraction of the star's surface, triggering the most energetic event we have ever detected from a stellar object at a confirmed distance. But while the general mechanism is established, the precise details remain difficult to model. How the magnetic field reaches and maintains this strength over the lifetime of the object, how energy accumulates in the crust without triggering premature discharge, and how the quantum mechanical behavior of matter under these conditions affects the overall dynamics. These are areas of active research with significant unresolved questions. The 2004 flare was not fully predicted. Its magnitude exceeded prior expectations, and the models that were used to describe magnetars before that event required revision afterward. What this object ultimately reveals is that our understanding of magnetic fields in extreme environments is still developing. We can describe the field strength. We can observe its effects. We can document the flares it produces. But the internal physics of a magnetar, the behavior of matter at these densities, under these field strengths, at the quantum mechanical level, remains only partially understood. The quantum critical field threshold has been formally crossed by this object, placing it in a regime where standard quantum electrodynamics must be extended and where laboratory verification is impossible. We are observing physics that our most sophisticated theories can approximate, but not yet fully describe. And that gap between approximation and full description matters, because it tells us something about where the boundaries of our knowledge actually sit. But magnetic fields, as extreme as they become in a magnetar, are a property that can at least be measured, categorized, and partially modeled. The final star on this list presents a different kind of challenge. Not a field we cannot fully explain, not a rotation rate that approaches a theoretical limit, a star that is actively destroying itself, shedding mass at a rate so extreme that astronomers have struggled for decades to construct a model that fully accounts for its structure, its behavior, and the sheer scale of its disintegration. A star that, in every meaningful sense, should not still be here. And yet it is. Enormous, violent, and coming apart at the seams. Every star examined in this documentary has pushed against a specific boundary. One exceeded the size limits of stellar stability. Another surpassed the theoretical ceiling for stellar mass. One defied our expectations of how a star should behave across observable timescales. Another spun faster than the models comfortably permit. And one generated a magnetic field so powerful it restructured matter at the atomic level. In each case, the star in question existed at an extreme, pressing against a limit, challenging a model, exposing a gap in our understanding. But all of them, in their own way, were still holding together, still maintaining some form of structural integrity, however precarious. The final star on this list does not have that quality. It is not pressing against a limit. it has already passed one, and it is coming apart. To understand why this matters, it helps to revisit how stellar evolution is supposed to work. A massive star spends the majority of its life in a state of equilibrium on what astronomers call the main sequence, fusing hydrogen in its core, maintaining a stable balance between gravity and outward pressure. When the hydrogen in the core runs out, the star evolves. It expands. It becomes a red supergiant. During this phase, the star is still broadly structured, still following a predictable evolutionary path, still losing mass at rates our models can account for. Eventually, the core exhausts its remaining fuel, collapses, and the star ends its life in a supernova. This sequence is well established. It is one of the most thoroughly studied processes in astrophysics, and for the vast majority of massive stars, it proceeds more or less according to expectation. But there is a category of massive stars that does not follow a clean, predictable path through these late evolutionary stages. Stars that, rather than evolving smoothly toward their final collapse, instead become violently, chaotically unstable long before that endpoint is reached. These are stars in which the balance between gravity and radiation pressure has broken down in ways that produce irregular, asymmetric mass loss. Not the gradual, steady shedding of material that models predict, but explosive, episodic eruptions of matter that reshape the environment around the star in ways that bear no resemblance to standard theoretical descriptions. The surrounding space is not a clean bubble of stellar wind. It is a complex, irregular nebula of ejected material. Clumps, arcs, filaments, accumulated from eruptions that varied enormously in their intensity and direction. These stars are not dying cleanly, they are fragmenting. In the constellation Canis Majoris, approximately 3,900 light-years from Earth, there is a star that represents this category at its most extreme. It has been known to astronomers for centuries, documented in historical records as far back as the 17th century, and yet its true nature only became fully apparent with modern observational tools. This star is designated VY Canis Majoris, and by nearly every measurement we have made of it, it is one of the most structurally compromised stars in the observable galaxy. It is a red hypergiant, a classification reserved for stars that exceed even the mass and luminosity thresholds of ordinary red supergiants. Its radius is estimated at somewhere between 1,000 and 1,400 solar radii, placing it among the largest stars known, though with significant uncertainty in the measurement. Its luminosity is approximately 270,000 times that of the Sun. But it is not the raw scale of this object that makes it scientifically significant. It is its structure. Detailed observations made with instruments including the Hubble Space Telescope reveal that this star is not a symmetric object. It does not have the relatively uniform, spherical form that stellar models predict even for evolved supergiants. Instead, it is surrounded by an extraordinarily complex nebula of ejected material, asymmetric arcs, discrete knots of dense gas, extended filaments, distributed in patterns that suggest the mass loss driving these structures was not uniform in direction or intensity. The ejections appear to have originated from localized regions of the stellar surface at different times, producing material flows that are not consistent with any simple, symmetric wind model. The star has not been shedding mass evenly. It has been erupting. The mass loss rate of this object is among the highest ever measured for any star. Estimates place it at roughly 1 solar mass every 100 years, meaning it loses an amount of material equivalent to the entire mass of our Sun approximately every century. To put that in context, our Sun loses mass through its solar wind at a rate so slow that it would take trillions of years to shed a meaningful fraction of its total mass at that rate. This object is losing mass at a rate that is, by comparison, almost incomprehensibly faster. The material surrounding it reflects this history. The nebula that has accumulated around the star over the past few thousand years contains enough mass to form multiple stellar systems. It is not a smooth outflow. It is a record of successive, violent ejection events, each one depositing material at different velocities and in different directions, producing the layered, irregular structure that observers have mapped in detail. Some of the individual knots of material within this nebula are moving outward at speeds of up to 50 kilometers per second. They were not gently released. They were expelled. This behavior contradicts standard models of evolved stellar mass loss in several important ways. The asymmetry of the ejected material suggests that the mechanisms driving mass loss in this object are not well described by the smooth, radiation-driven wind models that apply to most massive stars. Something is causing localized regions of the surface to erupt preferentially, driving material outward in specific directions at specific times. The precise physical cause of this behavior remains a subject of active investigation. Convection on scales comparable to the star itself has been proposed as a contributing factor. Enormous convective cells, each one potentially larger than the entire orbit of Earth, churning material within the stellar envelope and periodically driving eruptions at the surface. But convective models alone do not fully reproduce the observed structure of the surrounding nebula. The scale, the asymmetry, and the episodic nature of the ejections suggest that multiple interacting physical processes are at work simultaneously. Processes that our current models of stellar structure do not fully capture. The result is a star whose evolutionary behavior does not fit neatly into any single theoretical framework, despite being one of the most extensively observed massive stars in the sky. The future of this object is somewhat clearer than its present behavior. It will not survive indefinitely in this state. The continued mass loss will gradually reduce its outer layers, altering its structure and evolutionary trajectory. At some point, within the next 100,000 years by most estimates, its core will exhaust the remaining nuclear fuel available to it. What follows will be a core collapse, and the resulting explosion will be among the most energetic events our galaxy has witnessed in recent astronomical history. Whether the collapse produces a neutron star, a magnetar, or collapses directly into a black hole depends on the mass of the core at the time of collapse, itself a function of how much material is shed in the intervening period. That uncertainty is revealing. Even predicting the death of a star we are actively observing in detail is complicated by the fact that its present behavior does not match the models we would use to make that prediction. We are watching a star in the process of an evolutionary transition we do not yet fully understand, approaching an endpoint whose precise form depends on variables we cannot yet measure with confidence. It is one of the most extraordinary situations in observational astronomy. A nearby, well-studied, extensively imaged star whose physics remain partially opaque. There is one final object, and it does not belong to the same story as the others, because every star examined so far is still, in some form, alive. This one already died, in front of human eyes, and then refused to stay dead. 7,500 light-years away, in the southern constellation of Carinae, there is not one star, but two. A monstrous primary of roughly 100 solar masses and a companion near 30, locked in a violent 5.5-year orbit around one another. Together they burn with the light of nearly 5 million suns. The system likely began its life heavier than 150 times the mass of the Sun, already near the absolute ceiling for how much matter a single star can gather and still ignite. Nothing else in this region of the galaxy comes close to it. By raw output, this is among the brightest stellar systems the entire Milky Way contains. Its name is Eta Carinae. The English astronomer Edmund Halley first recorded it in 1677 as a faint and ordinary star, easy to overlook. For a century and a half after that, it remained quiet. Then, beginning around 1837, it did something no star is supposed to do while astronomers are watching. It brightened. Not gradually, dramatically. Over the following years, it climbed until by April of 1843, it rivaled Sirius and stood as the second brightest star in the entire night sky, despite lying nearly 800 times farther away than Sirius does. People across the southern hemisphere looked up and saw it blazing where within living memory there had been almost nothing. This was not a nova. It was not a trick of dust or distance. The event that came to be called the Great Eruption was a genuine explosion. In roughly 2 decades, the system expelled somewhere between 10 and 45 times the mass of the Sun, entire suns worth of material, thrown outward at speeds reaching 650 kilometers per second. The radiation and kinetic energy released rivaled that of a supernova. By the standards of the rest of this list, that single sentence should be the end of the story. Because a supernova is death. It is the terminal event, the collapse of a core, the destruction of the star, the seeding of space with everything the star ever made. When a massive star releases that much energy, it is not supposed to be there afterward. There is no afterward. What happens next is not in question. Only when. Eta Carinae is one of the most likely stars in our galaxy to detonate as a real supernova, and given its staggering mass, perhaps as something rarer and far more violent, a hypernova, a supernova that could outshine every recorded stellar explosion in human history, bright enough to be seen in broad daylight and to cast faint shadows at night. It carries, in theory, the makings of a gamma-ray burst, a blade of radiation fired from its poles. But the system is tilted. Its axis does not point at us. If that blade is ever drawn, it will be aimed somewhere out across the galaxy, not at Earth. Probably. And it may already be over. Light takes 7,500 years to cross the distance between us, which means the system we observe tonight is an image of a long-vanished past. The final collapse could have happened millennia ago, before the first cities, before written language, its announcement still in transit, crossing the dark toward us at the speed of light. So we watch a star that has already exploded once and survived. We chart its slow return from the brink. We map the tomb it has been building for itself, layer by layer, out of its own discarded mass. And somewhere, out in that silence, a single wavefront may already be on its way, the light of the true ending, released long ago, traveling toward a sky where, on one ordinary night, a faint point in the southern constellation of Carinae will quietly begin to blaze, brighter than it has ever burned, brighter than anything in the dark around it, and this time, it will not stop. And yet Eta Carinae survived. The explosion that should have ended it was instead something it lived through. Both stars are still there, still orbiting, still burning. The Great Eruption released roughly a tenth of the energy of a true core collapse supernova, enough to obliterate almost anything, and the binary at the center emerged intact, scarred but whole. Astronomers have a name for objects like this. They call them supernova imposters. What it is, in the language of astronomers, is a luminous blue variable, one of the rarest and most fleeting classifications a star can hold, a brief and turbulent chapter that only the most massive stars ever reach, and one we have witnessed only a handful of times across the entire galaxy. It is a phase measured not in billions of years, but in mere tens of thousands, and we understand it poorly precisely because so few examples exist to study. And the matter Eta Carinae hurled into space was not ordinary outer atmosphere. It was processed material, carbon and oxygen forged deep in the star's interior and dredged upward. the half-finished ash of its own nuclear furnace, scattered now across light-years of space. The material it threw off did not vanish. It is still expanding outward today, visible in every modern telescope as one of the most distinctive shapes in the sky. Two enormous lobes of gas billowing in opposite directions from the central stars, joined at a narrow waist, like an hourglass sculpted out of light. This is the Homunculus Nebula, and it is, in the most literal sense, the wreckage of an explosion we watched happen. Its dual lobes are still racing outward at speeds approaching 4.5 million kilometers per hour, sculpted by the eruption that gave them shape nearly 2 centuries ago. And it was not the only eruption. Half a century after the Great Eruption, in the 1890s, the system convulsed again. A second, smaller outburst that flung out a fresh shell of gas now nested inside the first, a miniature echo astronomers call the Little Homunculus. Deeper still, buried in the surrounding nebula, lies evidence of an even older ejection, material blasted into space centuries before Halley ever caught sight of the star. Eta Carinae has not erupted once. It has done it again and again, across the ages, each convulsion layered over the last like rings inside a wound. After the Great Eruption peaked, the system faded. The expelled material condensed into dust, and that dust drew a veil across the stars, dimming them by a factor of hundreds until Eta Carinae slipped back beneath naked-eye visibility for most of a century. It hid. And then, slowly, beginning in the 20th century, it started to grow brighter again, climbing back toward visibility as the veil thinned, until today it once more hovers right at the edge of what the unaided eye can detect. Even now, in its quieter state, the two stars are not at peace. Every 5.5 years, the smaller companion swings in close on its stretched, elongated orbit, and the searing winds streaming off both stars slam together where they meet. The collision is so violent it heats the gas to millions of degrees and floods the system with X-rays. Then, at the moment of closest approach, those X-rays abruptly vanish, dropping into a deep minimum that lasts about 3 months before climbing back. It is a rhythm, a pulse, a buried heartbeat we can measure but cannot fully explain, keeping time on a clock that was set nearly 2 centuries ago. But the deepest mystery is not the heartbeat, or even the survival. It is that we cannot fully explain how it erupted in the first place. When light from the Great Eruption, reflected off distant clouds of interstellar dust, finally reached Earth more than a century late, in a phenomenon called a light echo, astronomers were able to read the temperature of the explosion itself. And it was wrong. The eruption was significantly cooler than any standard model of such an event permits. The very mechanism that drove one of the most violent stellar outbursts ever recorded does not match the physics we use to describe it. The two stars deepen the puzzle further. The perfect mirrored symmetry of those twin lobes cannot be produced by a single star casting off its outer layers. The shape demands a partner. Two bodies, interacting, shaping the explosion between them in ways that remain only partly understood. In other galaxies, the rare objects that flare this way almost always vanish soon after, collapsing into true supernova within months or years of their imposter outbursts. Eta Carinae has now outlived its own catastrophe by nearly 2 centuries. It broke that pattern, and no one is entirely certain why.